Okay, in this section, Chapter 7, Section 2, we're going to talk about extreme points, maxima and minima of linear functions. This is what we've seen before, is you have a region bounded by constraints, and you want to find where the cost function is maximized or minimized. And we saw in previous examples that these are always at corner points, and here we're going to call those extreme points. And just to introduce some mathematical terminology that can generalize to any number of dimensions. Okay, so we're taking our two-dimensional ideas and jacking them up to arbitrary number of dimensions. All right. So in the present section, we first discuss the problem of finding the extreme points of a bounded convex polyhedral set. Then we find out how to compute the maximum and minimum values of a linear function defined on such a set. Okay, we use the following notation. Polyhedral convex set C is the true set of a statement AX less than or equal to B, where A is an m by n matrix, X is an n component vector, and B is an m component column vector. All right, so we saw before that you take your constraint equations and write each one as a row in your matrix, and then you multiply those equations one by your vector of variables, x1, x2, and so on. Sorry, it's not so clear. And then for each one of those equations you get a constant result, which is b1, b2, and so on. So this is just a very concise way of stacking a number of equations together. Now in this case we have these dimensions m and n. M is the number of equations, n is the number of variables. So we can think of these equations as specifying a set in n-dimensional space. Now here I have equality, here he has inequality. Of course the set where you have equality is the boundary of the set where you have inequality. All right. So I hope that kind of pulls things together and relates that to what we've seen in previous sections. Alright, so the statement AX less than or equal to B is the conjunction, or you can say intersection, of the statements A1X less than or equal to B1, A2X less than or equal to B2, AMX less than or equal to BM, where A1 is the first row of this matrix, A2 is the second row, and so on. Alright, so that relates this statement to the matrix that we have here. Definition: we shall call the true set of the statement AIX equals BI the bounding hyperplane of the hash space AIX less than or equal to BI. So if you relate this definition to our two-dimensional examples, then each line that is the edge of a region is a bounding hyperplane. It doesn't look like a plane, but as I mentioned previously, if you have 3 dimensions instead of 2, these bounding sets will in fact be planes. And just to continue the trend, when we have dimensions higher than 2, we call them hyperplanes. All right. So example 3, section 1, the bounding hyperplanes of the polyhedral convex set. 3 boundary lines of the triangle are your bounding hyperplanes. Note these 3 lines intersect in pairs in 3 points, the vertices of the triangle. All right, so this is kind of a preview of what we're going to be talking about, extreme points. These extreme points are going to be intersections of bounding hyperplanes that define your convex set. So here's the definition. Let C be a polyhedral convex set defined by AX less than or equal to B. And you know, fancy words, but just be thinking in 2 dimensions. This is just a region bounded by lines. In 3 dimensions it's going to be a region bounded by planes, and so on. Alright, so C is polyhedral convex set defined by AX less than or equal to B, where X is an n component vector. So that's the number of dimensions we're working in. Then a point T is an extreme or corner point of C if A, it belongs to C, and B is the intersection of n bounding hyperplanes of C. Now, why does it say n here? Right, well, let's think about the two-dimensional case. In the two-dimensional case, which is the case we've been working with, we have n equals 2. The extreme points have always been the intersection of 2 lines. two lines, and in this case, the line serves as a hyperplane. Now, if you had 3 dimensions, then the bounding hyperplanes are going to be planes. So, how are you going to get a point from planes? Well, the intersection of 2 planes is a line. You may remember that from geometry. And in order to get a point, you need 3 planes. Just think about it. If I've got a plane here and another plane here, very bad drawing, but another plane here, it's going to intersect in a line across like that, right? And then if I want to get a point, I'm going to need to intersect that line with a 3rd plane and get a point. So to get a point will require 3 planes, right? So now you can think about why that is. Why is that? Because each plane corresponds to a linear equation in 3 unknowns. If you remember, 3 equations, 3 unknowns can have a unique solution, right? If you have 2 equations in 3 unknowns, you can't have a unique solution. But 3 equations in 3 unknowns has a unique solution. That's why you need 3 planes to determine 1 point. Now, what about 4 dimensions? Well, the same principle works. 4 equations, 4 unknowns also determines a unique solution in general. Not always, but in general. The planes have to be oriented in the right way. You may know about situations that the planes are parallel or so on, then you don't get 3 planes intersecting in 1 point. Same in 4 dimensions. You can have the analogy of parallel planes in 4 dimensions. But in general, 3 planes in 3 dimensions intersect in a point. 4 hyperplanes in 4 dimensions intersect in a point. So that's why in n dimensions, you need the intersection of n hyperplanes to determine a corner point or extreme point of your region. Now, in this paragraph on page 324, we relate the geometric features of the region to the algebraic regions, the algebraic features. Now, we just got through saying that the points, the corner points, are the intersection of 2 bounding hyperplanes. Those are 2 equations. So that's going to be a point. Any extreme point is going to be a point where 2 equations hold with 2 of the constraints hold with equality. Okay, so 2 of the constraints must hold with equality. If you're on a line, a bounding line, then only one of the equations is going to hold with equality, because this bounding hyperplane is one equation. The other 2 bounding hyperplanes are not satisfied. A point is going to satisfy the equation if it lies on the bounding hyperplane. So here we have 2 equalities, here we have 1 equality, and inside we have no equalities. But remember, each of the constraints is an inequality, so it's okay to have all less thans. You'll just be inside the region. Now, this part of the discussion on what page is that? 324, says that you can have bounding hyperplanes and have a case where your polyhedral convex set is unbounded, say in the case where you have this, this, and this. So it's possible to have unbounded, and it's also possible to have bounded. And we've seen that before in the n-cert examples. All right, so that's fine. So I'm going to skip this example and go down to here. Now, so what's the big deal about extreme points? Well, it turns out that they're key in finding the extreme values, or maxima and minima, of linear functions. So given any convex polyhedral set C and any linear function that is a linear combination of n variables, right? This convex polyhedral set must be in n dimensions. N-dimensional convex polyhedral set and a linear function. You want to show that the maximum and minimum values of this linear function will always occur at extreme points of C. And of course, it's better to start with the easier case. So we carry out the proof for the planar case where n equals 2, but our results are true in general. Okay. So first, we shall show that the values of the linear function c1x1 plus c2x2 on any line segment lie between the values of the function has at the two endpoints. Okay, and may be equal to the value at one endpoint. So what we have is a line segment with two endpoints, and let's call those two endpoints P and Q, with x1 prime, x2 prime as the P, and x1 double prime, x2 double prime as the Q. Let me switch over to OneNote so we can draw this. So here's my P and my Q, and this, and of course here we have the x1, x2 plane, and then this point we're going to call this x1 prime, x2 prime, and this point is x1 double prime, x2 double prime. All right, so let's continue with the discussion. The discussion says, here he does column vectors, I'm doing row vectors, it's the same thing. Okay. So we've talked about how any point in between P and Q is this convex, what we call a convex linear combination of P and Q. It's T times P plus 1 minus T times Q, where T is between 0 and 1. You can see that by setting T equal to 1. If T equals 1, then this expression gives me P. If T equals 0, then this expression gives me Q. And everything else is a linear combination of P and Q, which means that it's on a straight line. Okay. So any value in the middle here is going to have, any point in the middle here is going to be TP plus 1 minus T times Q. Oh, just to make this clear, this P is a vector, this Q is a vector, and this is a sum of vectors. So this point is also a vector. All right. Now remember what we're trying to show. We're trying to show that this linear function at any point between P and Q is going to take a value between the linear function's value at P and the linear function's value at Q. It's going to take a value between those two. So let's follow the argument here. All right, so we have this. Okay. All right, so if the values of the function at points P and Q are big P and big Q respectively, and we can assume that big P is greater than or equal to big Q. If not, then we just switch the points around. Then a point in between the value would be T times big P plus 1 minus T times big Q, since the function is linear. You can actually work that out more explicitly. If you go back here, the value of the function here is going to be Cx1 prime, C1 x1 prime plus C2 x2 prime. The value of the function here is going to be C1 x1 double prime plus C2 x2 double prime. The value of the function here is going to be, well, if I actually work this out for the two components, the x1 component is going to be Tx1 prime plus 1 minus T x1 double prime. That's the convex combination of the x coordinates. And then for the x2 coordinates, it's the same thing. It's going to be T x2 prime plus 1 minus T times x2 double prime. All right. So at this point, the value of the function is going to be C1 times this first component, which is Tx1 prime plus 1 minus T x1 double prime plus C2, running out of space here, sorry, Tx2 prime plus 1 minus T x2 double prime. Sorry. All right, now if you simplify this expression here, just to make it clear, I'll just say if I simplify this expression here, I can factor out the terms with a T, and I can factor out the terms with a 1 minus T separately. If I factor out the terms with the T, there's the C1 Tx1 prime plus C2 Tx2 prime. So that's going to be T times C1 x1 prime plus C2 x2 prime. And then I have the 1 minus T, times C1 x1 double prime plus C2 x2 double prime, right? Now, but we've seen these expressions in square brackets before. If we call this P, then this is T times P. That's a big P rather. Okay, we call this big P, that's a big P rather. And this is 1 minus T. If I call this big Q here, then this is 1 minus T times big Q. All right. So if you actually work out the components and then break it apart algebraically, you can prove this formula here, that the value of the function is T times big P plus 1 minus T times big Q. All right. Now, this value is going to be between big P and big Q. When T equals 0, the value is big P. I'm sorry, when T equals 1, the value is big P. When T equals 0, the value is big Q. And then in between, it's going to be value in between. You can see that here. You can rewrite that as Q plus P minus Q times T. So it can't be bigger than Q. It can't be bigger than P, and it's bigger than Q. So we've proven that the values of the function on this line segment joining these 2 points are between the value of the function at the extreme points. Okay? So if I have a line segment and I want to know where the linear function is biggest, it has to be biggest at one of the 2 endpoints, at least one of the 2 endpoints. It could be biggest at this one, it could be biggest at this one, it could be biggest at both. If it's biggest at both, then it's a constant along this line. All right? So if I want to find maxima functions along a line segment, then I look at one of the 2 endpoints. Now that's not quite what we want. We want the maximum of a function in a region. Now if we knew the maximum was on the boundary, then we could say, well, if it's a maximum here, it also has to be maximum here because at one of these 2 points, because the value at one of these 2 points must be at least as big as this value, right? The extreme value must be at one of the endpoints, right? But we don't know that the extreme point is on the boundary, but that's where we're heading to next in the next part of the proof. We'll show that in fact the extreme point must be on the boundary. So here's the proof statement. A linear function Cx defined over a convex polyhedral set C takes it on its maximum and minimum value and on an extreme point of C. All right. So the proof of the theorem is illustrated in figure 5. Here's your convex polyhedral region. And suppose the value of the function is largest at this extreme point here. Now, how would you find the extreme point at which the value of the function is largest? Well, you just go around all the extreme points, evaluate the function, and take the biggest one. So suppose the value of the extreme point with largest value is here at P. Okay? Now take any other value, any other point in the polygon. Take this point R and draw the line segment joining P to R, and that line segment, if this is a bounded convex region, then it has to stop somewhere, otherwise the line would go on forever, so it must hit the boundary at one other point. Actually, you can prove that it has to meet the boundary at exactly one other point. He kind of sloughs over that point, but it's true. It has to meet the boundary at exactly one other point. So we have a line segment where the 2 endpoints are on the boundary of the convex set. Right? So we know that this one has the largest value corner point. This one is on the boundary. Now this one is going to be on a line segment between 2 corner points. And we just got through proving that the value of the function on this line segment must be largest at one or the other of these corner points. But the value of the function at one or the other of these corner points cannot be any larger than the value at this corner point. So in other words, the value at this corner point is bigger than or equal to the value here so it must be bigger than or equal to the value at R. And since R was any point within the convex region, P must be the maximum value for the entire convex region. All right. You can read through the proof more carefully, but that's the idea. That once you chose the maximum corner point, join it to any line, and then do this two-step argument to show that, in fact, the value at R must be less than or equal to the value at P. Now, the point here is that suppose to this linear function we add a constant. Well, if you add a constant to this linear function, then you're adding a constant everywhere. It doesn't change the relative size of the functional value. If this value is bigger than this one, and if I add k to both values, this value is still bigger than this one, right? Because I'm just adding k everywhere. It's like you're raising the floor. If you're raising the floor, then everything looks just the same. You don't see any difference. So we have the same result for this function cx plus k. That if you have linear expression cx and then you add a k, then the maximum or minimum value of this function will also be at an extreme point of c. Right. Now, method for finding the extreme maximum or minimum value for this function is similar to the other one. Go through all the extreme points, find the extreme value, and that will be the extreme value for the entire convex set. Okay. So in fact, there's a method called the simplex method, which is a much better method than going through all the extreme points. Basically, what the simplex method does is it walks from extreme point to extreme point. Along the, for instance, if you have this convex polyhedron, the simplex method walks from extreme point to extreme point till it finds the biggest one, and then it stops because it doesn't have to go through all of them. It just has to find the extreme point. And it's also very smart. It walks in a good direction rather than a bad direction. So let's stop there, and we're good.